Welcome to the session where we learn about a key technology of modern computer architecture, caches. They're a technology to tackle the von Neumann bottleneck and hence to make computers fast. They also have a massive impact on the way we shall think about implementations and write code. Caches are predominantly a CPU technology. Modern GPUs, however, use caches too, and indeed, cache-aware implementation ideas pay off immediately on the GPU as well. Let's start by introducing a few technical terms. When we speak of bandwidth, it refers to the number of bytes per second that a connection between two system parts can deliver. Think of it like a street. If there is space for 4 cars side by side on a street, then the street can accommodate, let's say, 100 cars per second. Now, if another street has only 2 lanes instead of 4, it might only manage 50 cars per second. And then there's latency, which refers to how long it takes for the first car to arrive. Let's imagine you're driving from Durham to York. It doesn't matter how wide the road is, latency is the time it takes for the first car to reach York. Together, latency and bandwidth determine how quickly you can transfer data within a system. In our von Neumann architecture, the ALU has to fetch data through the bus from the memory and write it back. Latency and bandwidth determine how fast this process is. The ALU's megaflop rate, in contrast, tells us how quick the actual computation runs. Together, the 3 ingredients determine how fast the calculation completes. As long as data resides within the registers on the ALU, we basically only pay for the compute. This allows us to distinguish 2 types of codes. Compute-bound code. This is when the ALU, the part of the system that performs calculations, is working at full capacity. It's so busy performing calculations that we are essentially waiting for the ALU to finish its work. Memory-bound code. In these cases, the ALU isn't the bottleneck. Instead, the system spends most of its time waiting for data to arrive, either due to bandwidth or latency limitations. Today, most codes are memory-bound. Modern CPUs can complete hundreds of floating point operations before data arrives from main memory, so bus and memory are permanently under pressure. Let's use this as a motivation to introduce a new concept. For this, let's dive deeper into the concept of memory-bound calculations and how we can address the inefficiencies they introduce. Imagine we have our worker, Mrs. ALU, sitting in her office, which represents the computational core. We previously discussed that there are only a limited number of registers available in the office. Now, every time Mrs. ALU needs to perform a task, such as adding 2 pieces of data, she might have to leave the office, run down to the basement, our main memory, sift through all the files on the shelves, retrieve the needed documents and climb up the stairs. As you can imagine, this is a slow and expensive process. Mrs. ALU does not spend much time in the office. She is busy climbing stairs, this is our boss, and getting documents. Her code is memory bound. To improve the situation, we can introduce an intermediate storage space, a smaller, closer room right outside the office. Let's call it the anteroom. This anteroom allows Mrs. ALU to store a handful of files nearby, so she doesn't always have to make all the long trip down into the basement. While the anteroom isn't as fast as having files directly on the desks, that's the registers, it's significantly quicker than accessing the basement. Whenever a document is not in the register but in the anteroom, we save a lot of time. This anteroom has to be small. It can only hold a few thousand files, not millions. The smaller the anteroom, the faster the lookup, but a larger anteroom reduces the need to visit the basement as often. Let's now translate this analogy into computer architecture. We said Mrs. ALU represents the computational core or CPU. The basement is the main memory and the staircase is the bus connecting them. The anteroom we just introduced is what we call a cache, and its size is the capacity of the cache. Whenever we are looking for a document in this room, we will call that a cache access. If the required data is found there, it's a cache hit. Otherwise, it's a cache miss. We can very easily get a cache hit rate or cache miss rate by simply dividing the number of cache hits or cache misses by the number of cache accesses. Obviously, our cache also has a certain latency and bandwidth, but both are way better than the ones on the main memory connected through a bus. Mrs. ALU is a smart worker. Every time she goes down to the basement, she does not fetch only one document. She usually takes a whole folder and fetches 512 documents in one rush. This concept is called a cache line. So the data moved over the bus is not individual quantities, it's always a small continuous sequence. For various reasons, data might not reside in the cache when we need it. In this case, we have to go to the main memory. We distinguish three types of cache misses. Some people call this the 3C. Compulsory misses are the ones arising when we access data for the first time. The data has never been requested before and therefore is not in the caches yet. Capacity misses are those where data had been in the cache before. However, at one point the cache had been too full, we had to remove some data, and now we need exactly that piece of information again that we had just removed due to capacity issues. Finally, there's conflict misses. Hardware often cannot hold any cache line at any place in the cache. Certain lines can only be stored in certain cache spaces. We say the cache is not fully associative. Now, it can happen that we'd like to have two cache lines, but they only fit in one line of the cache. So we have to swap data in and out to resolve this conflict, even though we would, in an ideal world, like to keep both lines as there would be enough space in the cache. How caches exactly work internally is typically the secret of the vendor. However, we can measure cache behavior. And least recently used is usually a good heuristic model. If a system has to move data out of a cache, it will rather evict data that had not been used for a while instead of a brand new hot fetch. Code that works well with caches is code with high spatial and temporal locality of its data accesses. Temporal locality means that whenever we work with a piece of data, the probability is high that we will soon need this piece of data again. So, even if that data are not in registers anymore, when we need it next, there's a high probability that it is at least in the caches. Spatial locality means that whenever we load one piece of data, the probability is high that we next need data close by in main memory. Since we work with whole cache lines, we hence might have brought in that data already due to a previous access. An example of an algorithm with high spatial locality is a code where we stream a sequence of data sequentially through the core. Both high spatial and high temporal locality address capacity issues. If we get the spatial locality right, we can even reduce compulsory misses. Code that is tweaked to make good use of caches is called cache-optimized or cache-aware code. To quantify these properties, we can rely on something we call arithmetic intensity. Sometimes we say computational intensity. Arithmetic intensity means number of calculations, flops, per byte loaded or stored. So for example, if we compute A plus B and both are double precision, so 8 bytes, we load 16 bytes, we store 8 and do one calculation. The arithmetic intensity hence is 1 over 24. In half precision it becomes 1 over 12. If A is already in the cache as it is a value calculated shortly before, that means temporal locality, we raise the arithmetic intensity to 1 over 8. Whenever we have a good idea, it is natural to apply this one again. In the case of caches, that means let's have a very small, very fast cache right next to the core. This one has very small latency and huge bandwidth. Then let's have a slightly bigger, yet slightly slower one after that. And then another one, which is even bigger. We label this hierarchy as levels. Level 1 cache is the smallest and fastest, then comes level 2 and finally level 3. Whenever the ALU asks for data, we look for it in level 1. If it's not there, we look in level 2 and so forth. If successful, we move a cache line up the hierarchy. So data ripples through the cascade of cache levels, though details again differ from system to system. Caches in multi-core systems, as we will study them later, can become tricky. Per cache, we have to make a decision as of whether a cache is local to a processor or shared between them. Local means faster. However, if a cache is local and holds data requested from somewhere else, we have to invest quite some work. We have to get the data out of the cache, sync with a lower level, bring it back to the actual core's cache. Modern systems hence make the smaller caches local and the bigger ones shared, so they compromise. Logically, the hardware keeps the caches coherent, but for the performance it can make a huge difference how we hit the caches. Modern CPU hardware typically features 3 cache levels, but we can generalize this idea. Whenever we have some large storage somewhere that is expensive to access and a smaller, faster memory somewhere else, we can use the faster memory as a cache. We can move chunks of data there prior to first use, maybe in one big rush, and then write our code such that it has high spatial and temporal locality. In this sense, our main memory is also a cache, this time for the hard disk. The takeaway is, caching can also be a software tuning technique. Thanks for your attention and see you again soon.